Today we're going to start talking about proofs. Before you freak out, let's just talk about what a proof is. We're talking about simple proofs, and a proof is just a detailed explanation of why a mathematical fact is true. And when we say detailed, what we really mean is that it follows the basic rules of reasoning. Proven facts are called theorems, and simple theorems that we use over and over again we call lemmas. We won't see any lemmas today, but next time we will be talking about a particular lemma that we're going to use a lot. And even though you might not think, oh, in elementary school we're doing proofs, that's not unusual to think. Why would we be thinking about proofs in elementary school? But proofs in elementary school are informal. They can be done with models or pictures or numbers, but you want to know what's going on behind some of these things we're going to talk about, because students will want to know why some things are true. This is something that happens. So that's what today's focus is about, is proving some basic theorems about numbers that students might want to know. So this way you can explain it to them, even if you're not giving them an algebraic proof, which we're going to practice. But even if that's not what you're doing, this will give you the tools to demonstrate on a picture or model level what happens and why some things are true to your students. Okay, we're going to start with some definitions. We're going to start by talking about the definition of an even number, and we're going to go with an informal definition first. So here are some ways we can think about even numbers. It could be a number which occurs as we skip count by 2, or it can be a number where we know we can pair things up with no remainder, nothing left over. That's a really good manipulative way to think about it, because you could actually have things that you're pairing up, and so you have nothing left over. You might think an even number is a number whose last digit is 0, 2, 4, or 6. Or you can think of it as a number which is twice a whole number. And in fact, that is our formal definition, is that an even number is a number which is twice a whole number. But when we talk about even numbers, we also need to talk about odd numbers, and that leads us to our next definition, which is that an odd number is a number which is one more than twice a whole number. Now, let's just talk about proofs again for a minute to understand what we're doing here. So a proof of a mathematical statement is a detailed explanation of how that statement follows logically from statements already accepted as true. So a couple of points here. A proof is not an explanation of what the fact is. So for example, if we were talking about something involving triangles, a proof would not be an explanation of what the triangle is, that it's a three-sided closed figure in the plane. That's not a proof. That's an explanation of a fact. A proof is a chain of reasoning that explains why the fact is a consequence of the assumptions and previously known facts. Okay, one of our big tools for understanding the proofs of the theorems we're going to look at today is using a pictorial representation for an even number and an odd number. We're going to start by talking about even numbers, and using the idea that an even number of objects can be paired with no remainder, we can get a nice pictorial representation of even numbers that looks like this. And you could draw something like this on your page to fill in the blank on your handout. And the dot, dot, dot there indicate that the number of squares in the middle is not specified. So this represents just an arbitrary, unknown even number, but it is an even number. And we can see that we have everything paired up. That's why I use the two different colors here, because we have a gray and a white paired up all the way along. Now, our algebraic representation of an even number uses our definition that an even number is twice a whole number. So we say an even number is 2k, where k is a whole number. So this is what we're going to use whenever we're doing algebraic proofs. Now on to odd numbers. we want our pictorial representation. So using our idea that an odd number is one more than an even number, we can picture it as objects that can be paired with no remainder and then plus one more. So it's going to be an even number, that's objects paired with no remainder, plus one. So in our picture we see we have objects paired with no remainder until we get to the end where we have remainder 1. You could also think of this as being paired with remainder 1. And again, the dot 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 indicate that the number of squares in the middle is not specified. So this represents just any odd number. The algebraic representation of an odd number uses the definition that an odd number is one more than twice a whole number. So an odd number is 2 times L plus 1, where L is a whole number. And this is what we'll be using when we're using representations, the algebraic representation when we're doing our proofs. And that will be in both the handout and presentation today and in your homework. Okay, our first theorem. The sum of 2 even numbers is even. So we're going to start out with just our picture proof. So here's just an even number, and we're going to add to it another even number. And notice I use different colors here, and if you notice, a different number of boxes to represent 2 different even numbers. We don't know what they are. They might even be the same even numbers, but we don't know that. We can't assume that. So I'm using the different colors to represent one even number and another even number. And we're going to add them together, and when we add them together, we're just going to stick the 2 rectangular arrays that we have here together like this. And now the total is even, and we can see that it's even because we have 2 rows that are exactly the same size. So everything gets paired together with no remainder. Now we're going to do the algebraic proof. And I want you to pay attention as we go through the algebraic proofs that the format is always the same. We're going to start out here. We're going to prove the sum of 2 even numbers is even. So we're going to let 2k and 2m be any 2 even numbers, where k and m are whole numbers. And then because we want to prove something about the sum of them, we are going to add these 2 even numbers together. So we have 2k plus 2m, and we're going to rewrite that as 2 times the quantity k plus m. And that's true by the distributive property. So the sum, which is 2k plus 2m, is even. So the sum is even since k plus m is a whole number, and we can write 2k plus 2m as 2 times a whole number. And there's our algebraic proof. So you should fill this in on your page on the handout as well. All right, our next theorem, the sum of an even number and an odd number is an odd number. We'll start again with our picture proof. First, we have an even number, and we're going to add to it an odd number. So we've got our picture representation of the odd number. And then when we add those together, we're going to stick those 2 arrays together so that they're side by side. And we get something where the total is odd. And we see that it's odd because our top row and our bottom row pair up until we get to that last square on the bottom right. And so we have evenly paired plus 1. So the total is odd. All right, now we're going to do the algebraic proof. And we're going to start out in the same manner we did in the previous proof. We're going to start by saying what the algebraic representation of each number involved is. So we're going to let 2k be an even number and 2m plus 1 be an odd number, where k and m are whole numbers. So that is using our algebraic representation of an even number and the algebraic representation of an odd number. And then because we want to know about their sum, we're going to add them together. So we get 2k plus 2m plus 1. And now we're going to rewrite that. We're going to use the distributive property and write that as 2 times the quantity k plus m plus 1. So that's by the distributive property. So the sum, 2k plus 2m plus 1, is odd since k plus m is a whole number, and we were able to write the sum as 2 times a whole number plus 1. And again, you should write that down on your handout. So theorem, last theorem of the day, I think. The sum of 2 odd numbers is an even number. We're going to start with our picture proof here. We're going to start with one odd number. We're going to add another odd number to it. So we've got our 2 different colors again to represent those 2 different odd numbers. We're going to add them together. We're just going to shove those 2 rectangular arrays together, and we get something that looks like this. And the total is even. We can see everything pairs up in the first rectangular array except that one left over. And then we have everything pairing up in the second rectangular array in green except the one left over. And so the white leftover and the green leftover pair up. So to see that a little more clearly, we're going to flip that second rectangular array around. So we have our odd number with the white rectangular array. We flip the second one, the green one, around just so they line up a little bit better. And then our even, the last array, when we shove those 2 together, we see right there where the white rectangular, the white box left over and the green box left over line up right together. And we can see that our total is even because everything is perfectly paired up. Okay, last bit, we are going to do the algebraic proof. And again, we're going to start out with our algebraic representations of the 2 numbers involved. So we have 2 odd numbers, so we have 2k plus 1 and 2m plus 1. Those are any 2 odd numbers because k and m are whole numbers. Then we're going to add those 2 together because we're looking at the sum of 2 odd numbers. So we have 2k plus 1 plus 2m plus 1. So that's equal to 2k plus 2m plus 2, just adding all of those bits together. And using the distributive property, we get 2 times the quantity k plus m plus 1. So the sum, 2k plus 1 plus 2m plus 1, is even since k plus m plus 1 is a whole number, and we were able to write the sum as 2 times a whole number. And that's it for now. But you want to keep these things in mind, both the picture proofs and the algebraic proofs and how this went, because when you do your homework, you're going to be drawing some pictures, and then you're also going to be doing some algebraic proofs. So you want the format to be basically the same.